Hi everyone, we'll begin in just a few minutes. Hi everyone, and welcome to everyone that's joined us today. Good morning or good afternoon, depending on where you're located. We're really glad to have you here at this Arving webinar about hydrogen storage. I'm Autumn Jarami, and I'll be the host for this webinar.
Hello everyone, I'm José Lombardo, co-author of this webinar and the instructor of some hydrogen courses here at Arving. Autumn will be delivering this webinar while I may join in here and there, in particular for the Q&A session.
Okay, thank you. So in this webinar, we're going to see an overview of the different technologies used to store hydrogen. It won't be an overly technical presentation, but rather an opportunity to review the different solutions to store hydrogen in gaseous, liquid, or even solid form. This webinar will be recorded and will be available here on our YouTube channel after the presentation, all right? At the end of the presentation, we'll have a Q&A session where you can ask questions either by the chat here on YouTube or by email, which is info@arvinggroup.com. And you can ask Jose your questions directly. He'll be answering them. So before we dive into today's topic, let's just briefly introduce ourselves. We are Arving Training and Engineering. As our name would suggest, we're a company that provides training as well as specialized engineering services. Our training is technical in nature, mainly focused on There we go. As our name would suggest, we're a company that provides specialized training and specialized engineering services. Our training is technical in nature, mainly focused on engineering topics. We're one of just a very few centers worldwide and the only center in Spain authorized by ASME, that is the American Society of Mechanical Engineers, to provide training about their codes and standards. On the engineering side, we develop projects related to the design of mechanical equipment, such as pressure vessels, complete piping systems, and more. We also do advanced analysis such as finite element analysis, fatigue analysis, and creep. And of course, we also offer technical assistance on topics such as forensic engineering and fitness for service analysis. Our direct relationship with ASME, in this sense, gives our specialized engineering services an important added value. So be sure to contact us with all your needs for specialized mechanical engineering or to help you fill in the gap in technical training for you, your company, or your project. We're a European company with clients from many different industries, many of them in the energy industry, from all over the world. We love a technical challenge. That being said, let's get back to our webinar. Today, we're going to delve into the topic of hydrogen storage. Specifically, we'll make an overview of how to store gaseous hydrogen, starting with the different mechanisms to compress it, its storage in pressure vessels or, on a massive scale, in underground reservoirs. We'll see the alternative of storing liquid hydrogen, touching upon its physical conditions and the type of tanks needed to store it. Storage in such carriers like ammonia, methanol, or other organic carriers, and the option of storage in solids such as metal hydrides or carbon structures. Finally, we'll touch upon the concept of levelized cost of storage. Let's begin by talking about gaseous hydrogen, which must be compressed in order to be stored. Hydrogen is generally produced at low pressures between 5 and 30 bar. Under these conditions, it occupies a large volume per unit of weight. How much space does 1 kilogram of hydrogen take up? Let's keep in mind the following general ideas. 1 kilogram of hydrogen at atmospheric pressure would occupy 11 cubic meters, which is 11,000 liters, the approximate volume of a small room. At 350 bar, the same amount of H2 would occupy 38 liters, similar to the size of a large oven. And at 700 bar, it would take up around 24 liters, roughly the size of a camping fridge. Why do we refer to these specific pressures? Well, it's because they're the pressures at which hydrogen is stored in vehicles. The Toyota Mirai, for example, stores about 5 kilograms of hydrogen at 700 bar. Now let's talk about compression. The curves in this graph represent the energy required to compress 1 kilogram of gas for both air and hydrogen. It's clear that hydrogen requires more energy per kilogram than air. We can also clearly see the much greater inefficiency of isotropic compression versus the ideal compression carried out at a constant temperature. For example, hydrogen compression up to 1,000 bar requires 2.6 kilowatt hours per kilogram for ideal isothermal compression and 8.6 kilowatt hours per kilogram for isotropic compression. The mechanism to bring the upper curve closer to the lower one is to carry out a multi-stage compression with intermediate cooling. This brings the process to an intermediate thermodynamic point, although with greater mechanical losses. There are different mechanisms to compress hydrogen, but it's possible to divide them into two large categories: mechanical compression and physical-chemical methods, with the latter still in the development phase. Let's take a look at these two broad categories. The mechanical compressors most commonly used to increase the pressure of hydrogen for storage are the reciprocating compressor, the diaphragm compressor, and the ionic compressor. Reciprocating compressors use a motor with a linear drive to move a piston back and forth. This movement compresses the hydrogen by reducing the volume it occupies. Reciprocating compressors are generally used for applications that require a very high compression ratio. It's a mature technology that adapts to different flow rates and has a high discharge pressure. Some of its disadvantages include the risk of hydrogen contamination by lubricating oils, the risk of metal embrittlement, and the complexity of its parts. Now on to diaphragm compressors, which also use a motor that produces a linear drive, but without direct contact with the hydrogen. The pressure variation is transmitted by an intermediate fluid and a flexible diaphragm that isolates the hydrogen from the rest of the system. It's a system that allows for high flow rates with relatively low energy consumption. It's suitable for handling explosive gases or gases that require high purity. Its drawbacks come from the risk of diaphragm failure and its more complex design. Ionic compressors are similar to reciprocating compressors, but use ionic liquids in place of the piston. These compressors do not require bearings and seals, two common sources of failure in reciprocating compressors. An ionic liquid compressor takes advantage of two properties of ionic liquids: their broad temperature range for their liquid phase and the low solubility of some gases, such as hydrogen, in them. This insolubility is exploited by using the body of an ionic liquid to compress hydrogen up to 1,000 bar. The Lind ionic liquid compressor reduced the number of moving parts from around 500 in a conventional reciprocating compressor to only 8. The centrifugal compressor used to moderately increase the pressure in transport pipelines, rather than for storage purposes. All right. Now about non-mechanical compression methods, which are still under development. They aim to exploit the properties of hydrogen in order to compress it without the need to convert electrical into mechanical power, thus saving some energy, reducing the number of moving parts, and in theory, improving efficiency. Hydride compressors use metals that combine with hydrogen to form hydrides through exothermic reactions and release hydrogen at high pressures when heat is applied. The real advantage of metal hydride compressors is that the energy powering the system can be derived from industrial heat waste rather than electricity. This can reduce operating costs. High-pressure hydrogen can be obtained in situ from water by connecting metal hydride compressors to the outlet of an electrolyzer and thereby recovering heat losses from the electrolyzer itself. The efficiency of a hydrogen metal hydride compressor is generally less than 25%. Similarly, other compressors are being developed based on the adsorption of hydrogen in very porous substances with a high specific surface area. Low-pressure hydrogen is fed to a closed tank filled with a solid bed of the porous material. Heat is then supplied to the system, causing hydrogen desorption to occur at a higher pressure. By forming a stack of membranes, it's possible to reach up to 1,000 bar. The efficiency could reach between 70 and 80%. These compressors are compact and have no moving parts. However, the progressive degradation of the membrane restricts the useful life to well below that of a mechanical compression device. An even more sophisticated alternative is the use of cryocompressors. The hydrogen is brought to a liquid state, and the pressure of the liquid is increased, but before being re-vaporized. With this system, very high efficiencies could be achieved, but the cost is still very high. Oh, I was a little back on the presentation, sorry. All right, the most common way to store hydrogen is in pressurized gas cylinders. Now that we've seen different systems to compress hydrogen, let's take a look at the cylinders themselves. Since the beginning of the last century, hydrogen has been stored in seamless steel cylinders. Around the late 1960s, aluminum cylinders also began to be used. To achieve higher pressures and lower weight, external reinforcements with rings were used, evolving towards a complete coating. There are 5 classified types of hydrogen storage tanks. First, of course, is type 1. These are manufactured from an all-metal cylinder. They can reach very large sizes and are the least expensive. They're also the heaviest and generally operate at lower pressures than the others. Tanks built according to ASME Section 8 Division 1 typically have a maximum pressure of 200 bar. However, tanks built according to Divisions 2 or 3 can operate at pressures of up to 1,000 bar and even higher. The mass of metal required to contain the pressure in a Type 1 tank generally allows for only 1 to 2% hydrogen storage relative to the mass of the cylinder. Next is Type 2. These cylinders are metallic, wrapped in composite material rings. Like Type 1, the ratio of hydrogen to cylinder mass is low. These containers are also heavy and thick-walled. Standard tanks generally have a maximum pressure of 300 bar. Next, Type 3. These cylinders are made up of a thin metal layer called a liner, covered by composite materials. The composite materials withstand the mechanical stresses, while the liner prevents the passage of hydrogen. They have a capacity up to 4 times that of standard Type 1 tanks. This means that smaller, lighter cylinders can be used to store the same amount of hydrogen. They usually have a maximum pressure of 700 bar. Next is Type 4. These are similar to Type 3, but the liner is a polymer, for example, high-density polyethylene, instead of a metal. They are lighter and have an efficiency similar to Type 3. They do not support mechanical loads. Finally, we have Type 5. These tanks are made entirely of composite material. They are the lightest and have a theoretical maximum pressure of around 1,000 bar. There is also a coding system used to identify tank subtypes within each main type, depending on the reinforcing material, the matrix, and so on. As can be seen in this image, the cylinders have other protection elements, as well as valve systems for their external connection. It's common for them to be assembled into integrated schemes of several cylinders, although these can also be built individually with different sizes. Let's see a more concrete example. This is the type of tank developed by Toyota for its use in its hydrogen vehicles, such as the Toyota Mirai. Looking at the image, what type of tank is it? It's Type 4. Did you get it right? It has an internal polymeric liner and is covered entirely by carbon fiber. It's interesting to see the 6% indicated in this specification. This is the mass of the stored hydrogen relative to the total mass of the system. Even in this case, which is highly optimized to minimize weight, the amount of stored hydrogen is a relatively small percentage of the total weight. Naturally, part of the added weight in this case comes from the protection necessary in the event of a crash. According to Toyota, it withstands a shock 5 times greater than that of a steel tank. This company already markets these tanks, but not only for vehicles. They also offer tanks up to 2 meters in length and 70 centimeters in diameter that can store nearly 20 kilograms of hydrogen at 700 bar. Here we see an example of large volumes of gaseous hydrogen being stored in pressurized cylinders. This is a plant located in Puerto Llano, Spain. It produces hydrogen from a 20 megawatt electrolyzer to feed a fertilizer factory. Each of the 11 tanks has a volume of 133 cubic meters with a height of 23 meters and a diameter of 2.8 meters. The wall thickness is 47 millimeters. Its weight when empty is 77 tons, and each one can store 6 tons of hydrogen at 60 bar. This type of tank is designed according to the ASME Section 8 standard. Let's look at another example, this time with the use of pressure vessels in underground storage. This is the case of the Delphi system from the Valloret Company, a manufacturer of tubular systems. They have patented this storage method that can contain between 1 and 100 tons of hydrogen. The system includes the construction of an underground vault up to 100 meters deep, in which a system of tubes is housed to contain hydrogen at a high pressure. In this image, you can see the construction of the chamber from the surface. This is just one example of storing hydrogen under pressure using metal containers. It's interesting because it can store a significant amount of hydrogen without a large footprint. Continuing with gaseous hydrogen and the search for massive storage solutions, it's possible to make a parallel to natural gas underground storage technologies. Both for hydrogen and natural gas, underground storage can be done in depleted hydrocarbon reservoirs, in caverns, for example, built-in salt domes using high-pressure water, or in depleted aquifers. These forms of hydrogen storage are still considered to be under development, since the interactions of the injected hydrogen with the pre-existing products in the reservoir are not completely known. The greatest advancement is with the salt caverns. There are already some in operation and numerous other projects in development. They have the advantage of having an excellent seal with an essentially inert material. They can work at pressures of around 200 bar. In these caverns, the interaction of hydrogen is much less complex, since in theory it can only react with the salt of the cavern and with some of the residual water from its construction. The salt caverns are artificial cavities that are created in geological salt deposits. They're generally located at a depth between 500 and 1,500 meters, with a height of around 150 meters. To create the cavern, the salt must first be drilled. The second stage consists of injecting water to dissolve it. The resulting brine is then removed, leaving free space where hydrogen can be stored under pressure. This type of reservoir stores very large volumes of hydrogen safely and at a relatively low cost. As they're located at great depths, they provide a natural barrier that can help contain hydrogen and prevent leaks. Additionally, rock salt is a dense, stable material that can withstand high pressures and temperatures associated with hydrogen storage. This concept has not yet been demonstrated on a massive industrial scale, in part because it requires natural saline deposits in diverse geographical locations. The hydrogen extracted from the cavern to be consumed may also require subsequent separation processes if it requires high purity. At the time of preparing this material, there are currently 4 salt caverns operating as hydrogen storage in the world, feeding adjacent petrochemical plants. 3 of these caves are in the United States, and another, the oldest one, is in the United Kingdom. They handle volumes of around 500,000 cubic meters. Let's compare this with the 11 cylinders at the Puerto Llano plant, each of which has a capacity of 133 cubic meters. At similar pressures, each cavern would contain the same amount of hydrogen as about 4,000 of these enormous tanks. In the U.S., about 200 kilometers south of Salt Lake City, engineers are working on what will become the world's largest storage facility for up to 1,000 megawatts of clean energy. This will be done in part by storing hydrogen in underground salt caverns. The plant takes excess hydroelectric, geothermal, solar, and wind energy and electrolyzes it. It then stores the resulting hydrogen in twin salt caverns, where it will later be used for energy, industrial, and transportation purposes. The salt caverns are huge, around 700,000 cubic meters each. In Europe, there are some areas with potential for the development of salt caverns. This map shows some candidate as well as current underground reservoirs used for natural gas. The area with the greatest potential is in northwest Germany and the Netherlands. One example of a project under development is Hipster. In this project, located in France, hydrogen will be produced with a 1 megawatt electrolyzer. Storage will take place in a salt cavern capable of preserving more than 6,000 tons of hydrogen. So what about the rest of the world and these types of projects? The International Energy Agency has its own database dedicated to hydrogen projects. One of them is an Excel file that shows different infrastructure projects. It's divided into projects for pipelines, hydrogen blending, storage, and more. If we sort the sheet by starting date, the first one to appear is a project in Austria, then one in Argentina, and followed by the Netherlands and Sweden, and so on. All the projects that appear at the beginning are in demo mode. It's interesting to note that not all of the projects involve salt caverns. Some use depleted reservoirs where there's already a lot of experience storing natural gas. The total number of storage projects is minimal compared to the hydrogen production projects. The IEA recognizes that there is an important gap in this regard. All right, so now that we saw the possibility of storing hydrogen in the form of a gas, either in pressurized tanks or underground, let's see one way to obtain greater energy density by storing hydrogen in a liquid state. This is the comparison between gaseous hydrogen at different pressures that we saw previously, now with liquid hydrogen added. We can see that 1 kilogram of liquid hydrogen occupies only 14 liters compared to the 24 liters it occupies when compressed at 700 bar. To bring hydrogen to a liquid state, however, the temperature must be greatly reduced until it reaches negative 253 degrees Celsius. The process to bring hydrogen to that temperature consists of, first, a compression stage, then pre-cooling through heat exchangers. Next, liquefaction, where hydrogen passes through a series of heat exchanger and expansion turbines. In this stage, the gas is further cooled by passing it through a cascade of refrigerants, such as liquid helium or neon, which remove heat from the hydrogen gas, causing it to condense and turn into a liquid state. The final stage is expansion and separation. This process is very energy intensive. As seen in the graph, most of the energy is consumed by cryogenic cooling. That is, the jump from negative 190 degrees to negative 243 degrees Celsius, followed by pre-cooling, pre-compression, and the final expansion and separation. Current processes have specific energy consumption well above the ideal consumption, although there are theoretical plant designs that would be closer to it. These current processes have a consumption equivalent to around 40% of the lower heating value of hydrogen, which contributes to the high specific liquefaction cost. It would be in around $3 per kilogram. In short, obtaining liquid hydrogen is expensive and technologically complex. However, there is a lot of experience in this area because liquid hydrogen is used as a fuel in the aerospace industry. Liquid hydrogen is usually stored in horizontal or vertical cylindrical tanks, although there are also some spherical designs used for large volumes. A liquid hydrogen tank is composed of several layers to ensure its safe and efficient storage. A tank has the following components: an internal container where the liquid hydrogen is stored. It's usually made of stainless steel or aluminum, which can resist cryogenic temperatures and maintain liquid tightness. An external container, which surrounds the internal container and produces a layer of thermal insulation. It's designed to minimize heat transfer from the surrounding environment to the liquid hydrogen, helping to maintain the low temperatures required for storage. Between both containers, there's a layer of thermal insulation, generally made of materials such as expanded perlite, polyurethane foam, or fiberglass. This insulation helps prevent cold loss and keeps the temperature low inside the tank. The tank will also have valves, safety devices, sensors, and so on. The type of structural elements that support the internal tank can be tension-based or compression-based. Boil-off gas is an inevitable result of LH2 storage. A certain percentage of liquid hydrogen will eventually enter the gas phase, depending on factors such as wall material, quality of the insulation, and the surface to volume ratio of the container. Typical boil-off values range between 0.1% per day for larger spheres and up to 1% per day for smaller tanks. The most common design does not include active devices to prevent boil-off, although integrated refrigeration and storage systems have been developed aimed at maintaining the stored liquid in a state of zero evaporation. The largest LH2 tank in the world is from NASA, and it's at the Kennedy Space Center in Florida. It has a total capacity of 327 metric tons of hydrogen, exceeding the 263 metric tons of its predecessor, also from NASA and located at the same center. High vacuum insulation is commonly used for small tanks, and low vacuum insulation for larger tanks. Storage in a liquid state is not only used for large volumes. There are also hydrogen refueling stations, for example, that receive and store hydrogen in a liquid state. As an option for storage, and especially for transportation, is the use of hydrogen carriers such as ammonia or other organic carriers. One of the hydrogen carriers that attracts the most attention is ammonia. It's a simple molecule made up of 1 nitrogen and 3 hydrogen atoms. Under normal conditions, it's a colorless gas with a very pungent odor whose greatest risk is that it's a toxic substance at medium and high concentrations. For its storage and transportation, it's convenient to have it in a liquid state. This can be achieved in 2 different ways without the need for extreme conditions. At atmospheric pressure by reducing the temperature to 33 degrees below zero, or by raising the pressure to 7.5 bar at room temperature around 20 degrees Celsius. In both cases, liquid ammonia is obtained, but for safety reasons, the preferred method is liquefaction by reducing the temperature to negative 33 degrees C. It's interesting to note that the volumetric density of hydrogen achieved with liquid ammonia is significantly greater than that of hydrogen, which, when taken to the liquid phase at negative 253 degrees Celsius, reaches a density of 71 kilograms of hydrogen per cubic meter versus the 121 kilograms per cubic meter achieved with ammonia. In other words, with ammonia, much less volume is required for the same amount of hydrogen, without the need for extreme conditions. This is what makes it so attractive for use in the storage and transportation of hydrogen. Producing ammonia, however, is not free. The process starts by obtaining hydrogen through electrolysis and extracting nitrogen from the air through cryogenic distillation or by PSA. These 2 products are then combined in a process called Haber-Bosch process through a catalytic reaction at a temperature between 350 and 500 degrees Celsius. The energy consumption to produce ammonia is around 10 kilowatt-hours per kilogram of product. Once ammonia is obtained, its pure storage cost for periods longer than a few weeks will be much lower than that of liquid hydrogen or hydrogen compressed at very high temperatures. So, how is ammonia stored? Well, there are different tank structures that can be used to store ammonia. In the past, they were made with single walls with internal or external insulation. The current standard based on quantitative risk assessment is to use double walls. According to statistics from the UK, the frequency of failure with double walls is 100 times lower than with single walls. The double-walled, double-integrity tank with external insulation shown in this figure would allow the tank to operate longer until repaired in case of a failure. Another common construction method is the use of a double tank with insulation in the annular space. This option is more economical, but would require decommissioning the tank in case of an internal tank failure. In double-wall designs, the inner tank is designed to contain the entire nominal value. nominal volume. Both tanks are made of the same material, normalized carbon manganese steel. The support pylons under the tank are usually made of treated wood. These are preferable to concrete blocks at the bottom of the tank for insulation reasons. One of the greatest benefits of using ammonia for storage lies in the possibility of reusing the existing infrastructure for LPG storage. This figure shows a bilobular tank designed by Arvang for the storage of ammonia or LPG. As the existing infrastructure for ammonia storage is extensive, it can be further enhanced without great effort through the conversion of the LPG infrastructure. Another hydrogen carrier of great interest is methanol. It's an alcohol, thereby containing carbon, that remains liquid at room temperature. Its volumetric density is greater than that of liquid hydrogen, but lower than ammonia. The synthesis of methanol from green hydrogen requires the contribution of a stream of previously captured CO2. Two processes are used to synthesize methanol: direct and indirect chemical conversion of CO2. In the first, CO2 is directly converted to methanol, while in the second, CO2 is first converted to syngas in a reverse displacement reactor, where it's then used as a feedstock in the methanol reactor. The efficiency in the methanol synthesis process can range from between 40 to 70%. Guidelines for the design, fabrication, erection, repair, and protection of above-ground methanol storage tanks are essentially the same as those for liquid transportation fuels, with some specific considerations. An important consideration is the flammability range, which is much greater than that of gasoline. Methanol vapor presents a greater risk of igniting within the void space of the tank. Excuse me. Another consideration is corrosion. Galvanic and dissimilar metal corrosion in methanol service can be high if incompatible materials are brought into electrical contact with each other. Cathodic protection and inspection of internal components are vitally important to avoid corrosion failures. Organic liquid carriers are an option for storage, but even more so for the transportation of hydrogen. Their use is based on hydrogenating an unsaturated organic substance, that is, one that has double carbon bonds, by saturating it with hydrogen. This example shows toluene, C6H5CH3, which has 3 double bonds. When hydrogenated, it becomes methyl cyclohexane, a compound that has 6 additional hydrogen atoms in its molecule. There are other organic compounds that can be used in this cycle of hydrogenating for storage and transport and dehydrogenating for hydrogen use. This graph shows dibenzyltoluene, which, when hydrogenated with 9 hydrogen molecules, results in parahydrodibenzyltoluene. The volumetric density of LOHCs is less than that of liquid hydrogen. However, they're an attractive alternative for storing hydrogen because they're very stable liquids, not very flammable, low in toxicity, and quite importantly, they allow for the use of existing infrastructure for storage and transportation of liquid fuels. We saw the storage of hydrogen in gaseous and liquid states, and its storage in liquid carriers. Now let's see hydrogen stored in a solid state. As an alternative for very safe hydrogen storage, an alternative is through the use of metal hydrides. A solid metal structure, preferably made of lightweight metals such as magnesium, subjected to hydrogen under pressure, will undergo a chemical reaction where the hydrogen becomes embedded in the metal through covalent bonds. This process is exothermic, releasing heat that should be utilized to maximize efficiency. And the structure is very stable and secure. Applying heat to the hydrogen-loaded structure has the opposite effect, releasing the hydrogen for its consumption. The volumetric density reached is quite interesting, similar to that of LH2. The gravimetric density, however, is not so convenient due to the weight of the metal structure. To store 1.5 kilograms of hydrogen would require about 100 kilograms of metal. Compared to other hydrogen storage systems, this energy density is low, but it's comparable to a standard lithium battery, such as those used by electric vehicles. The biggest drawback that this solution faces are the high temperature necessary to release the hydrogen at around 300 degrees Celsius, the relative slowness of the absorption-desorption processes, and the degradation due to repetitive charge and discharge cycles. Its application is studied and developed for use in vehicles, homes, and buildings due to the safety offered by this storage, this solid and stable storage. In the Tyrolean cabins shown in the image, as well as in some submarines, hydrogen storage and metal hydrides is used. In this case, hydrogen is produced and stored from surplus hydroelectric energy in summer for use through fuel cells in winter. Numerous alternative methods of solid-state storage are being investigated, particularly in carbon structures. By primarily employing the principle of physical adsorption as opposed to the chemical absorption of metal hydrides, the charging process is much faster and completely reversible. Adsorption occurs by increasing pressure, while reducing this pressure leads to the release of hydrogen. These materials are lightweight, and the key to their use lies in achieving highly porous structures with high specific surface area. The most studied materials include the following. Activated carbons. These are carbonaceous materials with a large surface area and an internal structure composed of a series of pores and cavities. Activated carbons are obtained from materials such as coconut shells, wood, charcoal, or coal through an activation process involving thermal and/or chemical treatments. Carbon nanotubes. Discovered in 1991, they drove a lot of attention as a promising material for hydrogen storage applications. Nanotubes undergo treatment to make the inner part accessible for gas penetration and to increase the accessible surface area. Fullerenes. These spherical structures have been investigated as potential candidates for hydrogen storage due to their hollow interior and high surface area, which could provide sites for hydrogen adsorption. However, they have not proven to be a practical solution so far, as they exhibit less specific surface area than other alternatives. Hydrogen molecules diffuse into the C60 network without dissociating, resulting in around 0.2% by weight of H2. Graphene. This is a carbon material consisting of a layer of carbon atoms arranged in a hexagonal two-dimensional structure. On its own, it's not an ideal candidate for storing hydrogen due to its relatively weak adsorption. It could, however, be modified or combined with other materials to achieve high storage capacity, such as by developing nanopores or forming compounds. Metal organic framework materials. These are materials formed by metal ions connected with organic ligands, creating a three-dimensional structure. This structure provides a highly porous material with a large surface area and a network of interconnected channels and cavities. They're probably the most promising materials for hydrogen absorption through physisorption. Hydrogen storage capacities of up to 8.6% by weight have been reached. That's a record for physisorption processes. The gravimetric capacity is similar to activated carbons and nanotubes, but with a much more compact volume. All of these options are still in the research and development phase. We saw hydrogen storage methods. Now, to close out the webinar, let's briefly go over the concept of levelized cost of storage. And just as a reminder, you can send your questions through the chat or email us at info@arvanggroup.com for the Q&A session, which we'll hold shortly. Okay, on to the levelized cost of storage. The mathematical expression to determine the levelized cost of storage is similar to that known as LCOH, which is the levelized cost of hydrogen production. Conceptually, it represents the price as a constant for the entire life of the project that would have to be charged to cover all costs incurred due to storage, both investments and expenses, including abandonment costs. Ultimately, this value allows us to compare different projects or technologies against each other. In this example, we see some values identified by a project called High Stories, meaning hydrogen storage in European subsurface. In this project, geological sites in all European countries were analyzed, identifying the resulting storage costs using different technologies and involving other variables and conditions. A lot of variation can be seen between countries when storage in porous media is considered, that is, depleted hydrocarbon reservoirs or aquifers. For saline caverns, shown by triangles in the chart, the values are more homogeneous. Note the logarithmic scale used for the cost because the differences between the sites are quite significant. A simplified conclusion of this study is that it would be cheaper in the medium term to use depleted reservoirs to store hydrogen, 1.1 euros per kilogram compared to 2.3 for salt caverns. But the technological maturity of the salt caverns is greater, in part because the possible interaction of hydrogen with the minerals and fluids present in depleted reservoirs is still not well known. In summary, potentially the cheapest option, depleted hydrocarbon reservoirs. The more mature and feasible option in the medium term, salt caverns. If you're interested in underground storage, the High Stories website is a very interesting source of information. To sum up, we'll use a study carried out by Bloomberg, in this case more focused in the United States. Considerations when talking about storage should include the cost, of course, storage time, volume to be stored, geographical availability, and technological maturity. The main takeaway is this: the storage methods for hydrogen that will be most used in the coming decades will be saline caverns for storing large volumes for periods of months, for example, for seasonal energy balance, pressure vessels for daily storage of smaller volumes with hydrogen gas always under pressure. Other technologies such as ammonia or organic carriers will have a great role in the international transport of hydrogen, increasing its presence as an intermediate storage mechanism linked to the global supply chain. So now, here's a full summary of what we've seen in this webinar. We covered both mechanical and non-mechanical hydrogen compression systems, the storage of gaseous hydrogen in pressure vessels classified into types 1 through 5 based on their construction method and working pressure. We examined specific examples of storage for relatively high volumes in pressure vessels. Regarding underground storage, we highlighted the feasibility of using salt caverns compared to other alternatives being studied, such as depleted aquifers. But we noted that the number of large-scale storage projects is still limited. We explored the storage of hydrogen in liquid state at extremely cryogenic temperatures and reviewed the option of storing hydrogen in the form of ammonia, or the alternative of using methanol. We saw that liquid organic hydrogen carriers are yet another option to store hydrogen in a liquid state. We then moved on to solid-state alternatives, including metal hydrides and highly porous substances such as carbon structures or organometallic frameworks. So, all in all, we covered hydrogen storage in the form of gas, liquid, and solid. Finally, we touched upon the concept of levelized cost of storage, using some examples to conclude that the best options would be salt caverns for large volumes and extended periods, and pressure vessels for smaller volumes. So, thank you very much for your attention. We're going to now move on to the Q&A session. Give me 1 second. Here we have Jose Luis here to answer some of your questions. So you can, 1 second. Okay, so you can start putting them in the chat or email them to us. Jose Luis, we do have one question from Clinton. So he says, in terms of E&I control / monitoring, what are the important parameters that are required to be tracked or optimized in hydrogen storage systems?
I'm not sure I understand completely the question, since we have covered all type of systems for hydrogen storage. In terms of, we just are the very, very critical variables for storage. It's obvious that temperature and pressure are the key ones. Not only because of the, let's say, mechanical structure of the tank or whatever, but also because of the risk of embrittlement that comes with this relationship between pressure and temperature. Not only pressure at an absolute value, but also in the variation of pressure. The higher the number of cycles of pressure variation, the higher the risk of embrittlement. So these are the two main variables.
Okay, thank you. I also have a question that we received by email, wondering, is there any particular code for the design of hydrogen pressure vessels?
Well, there is no one particular code for the design of hydrogen pressure vessels, but you know that we are serving ASME training authorized suppliers. So ASME, Boiler and Pressure Vessel Code, Section 8, Division 3, has a particular note which is KD10 that is dedicated in particular for high pressure hydrogen. This note is not only used for the Boiler and Pressure Vessel Code, but also, for example, in B31.12, which is dedicated to hydrogen piping and pipelines.
Okay, thank you. So yeah, I see some movement in the chat, but you can keep sending your questions. And meanwhile, we'll take another one from email that says, will ammonia be the future for hydrogen storage? Can you let us know what you think about that?
Well, ammonia, will be key in terms of transportation of hydrogen. If you're producing hydrogen, let's say in Magallanes, in the south of the south, in Chile, and you want to move that hydrogen to Japan or to Europe, quite probably you will be using ammonia. So there will be important volumes of ammonia as storage, intermediate storage for hydrogen. However, to produce ammonia and to recover the hydrogen, you need energy. So we will see a lot of hydrogen storage being made, as you have mentioned in the webinar, in salt caverns and in metallic tanks.
Okay, great. We have just a little bit more time. We can take some more questions. So again, feel free to add them to the chat or to email us, as we mentioned. Another question is about the different types of cylinders that we saw. Wondering if the Type 5 cylinders are already on the market.
That's a good question. The answer is no, not yet, at least. I mean, there are some Type 5 cylinders in the market that are more dedicated to, for example, for the space industry, and starting to develop the use for other uses, such as cars or whatever. Let's say the top of the game today are Type 4, such as the one you shown that developed by Toyota, for example.
Okay, well, thank you so much, Jose Luis, for being the brains behind this webinar. And we want to thank everyone for joining us as well. We know that in the short time of a webinar, it's not enough to go too deep into such a broad topic. But do feel free to check out our courses. We have a whole course about the different technologies related to hydrogen. Oh, sorry, give me 1 second. We just got a question. Okay, we'll fit in this one last question before we finish up fully goodbye. Giuseppe says, is there any difference between the shapes of the vessels for storage? A sphere or a column, does it make a difference, the shape of the vessel?
Of course, there is difference. In general, let's say the commonwealth is to use a cylinder for storage of either low volumes of liquid hydrogen or in gaseous hydrogen in any form. In general, you see spheres only for liquid hydrogen at very, very high volumes, such as the one used by NASA, for example.
That's an interesting question. So again, like I was saying before, we thank everyone for joining us. We understand that the short time of a webinar is not enough to go too deep into this topic. That we could go on for a long time about it. But do feel free to check out our course about hydrogen technologies to learn more about that. And while you're at it, you can check out all the other courses on different topics we have available, all specialized engineering courses. And we remind you that if you want to go back and revisit some of the things we saw, that this will be available on our channel, on our YouTube channel. This one. And make sure you follow us on social media so that you can see when we do different events like webinars or launch new courses or have any types of events. So we hope that you have a good rest of the day wherever you may be. And we hope to see you at more Arving events and courses very soon. Bye, everyone.
Well, thank you, Autumn, and thank you all. Bye-bye.